right. Oh, it's always so loud. All right. So, hello, everyone. Good late afternoon. So, logistics-wise, as I hope to have the free response grades in at this point, but that has not come to fruition. So, I've sent a message to the grader to ask him, but hopefully we can have the grades in by the end of next week. If he responds before the end of the class, I'll give you all an update. If not, I'll give you an update once I hear from him about an ETA for that. Now, to that end, I mentioned this last class, I believe. Maybe not, maybe so. Whatever the free response grades are, so like the multiple choice, I can actually look at individual questions, and I could do a curve based upon was it me or was it you kind of thing, based upon how the average did and stuff like that. In this case, because I'm not the one grading 190 tests, I don't kind of have the information of where were the mistakes, is it me or is it you kind of situation. To that end, what I will be doing for a curve for the free response is if the average is below a 75, I will add points to get the average to a 75 for the average. Okay? If the average is above a 75, I won't touch it. I'm not going to lower it. So, you all can kind of have that for good or for bad. That's how the curve will work when I eventually do get them. So if there's a curve, it's to raise it up to 75, unless they already are above that 75. Yeah?
Same curve based off free response or is it
based off free response, just the free response portion. So I already curved the multiple choice kind of based upon how people responded there. The free response will have its own curve based upon how people did on that one. Okay? There is a very strong correlation between the multiple choice and free response, and every time I've given it, like they should be testing the same thing. So again, if you did decent on the multiple choice, you can expect that you probably did well in the free response, and the opposite is also true. If you didn't do well on the multiple choice, it's not very likely you'll do well on the free response. Now, because there is the partial credit and all of that, so again, I'll have to see, we'll have to see what the scores look like. I don't know yet, I haven't gotten them. My Physics 2 class, so they only had one question. Due to time limitations, they only had one free response to answer, whereas you all had to answer two. That may sound better, but more questions generally benefits you all. But due to how that class is Tuesday, Thursday, so they did their entire exam, free response and multiple choice, an hour, 20 minutes, whereas you all had 50 minutes free response, 50 minutes multiple choice, whatever. The reason I say that, their average on the multiple choice was actually lower than the average on the free response. So it could be that the free response average is actually higher than the multiple choice. That's the only data. We'll see. There's a lot of variables there. But the partial credit gives a lot of flexibility. If you knew what you were doing, you'll get the points, regardless if you made stupid mistakes here and there. If you knew what you were doing conceptually, if you did the givens, the missings, the right equation, that kind of thing, if you think back on it, I mean, at the end of the day, the problems I gave you all, a projectile motion problem, that pulley problem, the, what was the third one? The people moving. We did problems just like each of those. In every quiz, there was a problem like that. And so to that end, you all can look back at those quiz solutions and kind of have a sense of how you did, if you knew what you were doing or not. So we have examples you can go back and kind of self-grade yourself and have a sense of how you did on it. And if you felt like, yeah, when I looked at those solutions, that's what I did, great. That's a good sign. If you look at those solutions like, oh, I did not do that. Again, that kind of is indicative of what the grade will probably be on those. Okay? So there is some kind of ability to kind of self-check while you're waiting, if you're interested. Otherwise, the grades will post, hopefully, again. I'll let you know. I'll let you know when I know. All right, so today, we finished up energy. Yay! Last class, we got through energy. Just a reminder to you all, conservation of energy was basically take all the energy in the beginning, it equals all the energy in the end. That is always true. And then we had two kind of specific scenarios. If the energy is all if you have conservative forces, Potential and kinetic are conservative forces. Potential energy of gravity, potential energy of spring, kinetic energy, those are all conservative. If that's the only thing that you have, if you do not have friction, if you do not have air resistance, then what you start with is what you end with. And we did a problem like that. What you start with is what you end with. We actually did 2 problems like that. So that was one case. Conservative forces, aka no friction, no air resistance. What you start with is what you end with. Done. If there's friction, very similar. What you start with is what you end with, but we just have a little bit of an extra. Some energy is lost to friction. We call that the work due to friction, and that's on the left side. Or you can do it this way, and this is the way I kind of like to do it. Think about it. Take the final energy, so add up all the kinetic and potentials, final. Add up all the kinetic and potentials, initial, subtract those 2. Oh, look, there's a different number. Where'd the energy go? Work due to friction. Heat, sound, vibrations, things you cannot recover. You cannot recover the energy lost to friction. You cannot recover the energy lost to heat. For the most part, again, I'm saying that as like a hand wavy thing. Not easily. Okay? And then we did some math problems with this. Definitely look through those. Conservation of energy, though, is a fairly straightforward process. This, in my opinion, is one of the easier topics that gets kind of covered. The math isn't really that bad. The setup really is that initial equals final, plug and chug. So try these out. If you don't feel the same way, that's okay. Easy or difficult is all relative. But it's scalars, so that's nice. No vectors. All right. Does anyone have any questions about energy? Because that was a great time to ask. We're not in a rush. All right. Well, we had so much fun with scalars. Well, they're gone. Back to vectors. All right. So we're going to start momentum. This is technically kind of scheduled. Like the plan was to start this next week, but by starting now, that just means that we have more flex time. We can go at a slower pace. We don't need to rush. Momentum, in my opinion, is also fairly straightforward. Momentum, in my opinion, won't be that. It's going to be like conservation of energy, but replace the word energy with momentum. And then just remember you have to split into X and Y components. So it should kind of build nicely on it. So yeah, we're going to learn what momentum is. Fun fact, it's also a made-up thing, like energy. So yay or nay, whatever you put on it. We're going to figure out how to calculate it. We're going to talk about impulses and how it relates to collisions and the velocity. And then we're going to explain how momentum is conserved, conservation momentum, and use this to calculate things. Velocity specifically. So momentum is all about collisions. Basically, if anything collides in any problem I ever give you, it's a momentum problem. If there's a collision of 2 things hitting each other, your mind should immediately go, this is momentum. That's kind of the trigger. Collisions, there's momentum. If you're talking about something changing its height, then your mind should go to conservation of energy. Or if there's a spring involved, your mind should go to conservation of energy. So those are the little kind of triggers that tell you how you should proceed. So things you need to remember, vectors, they are back. As far as them being back, you just need to remember to split things into X and Y. That's all you need to know here. X, Y independence. And then the kinematic equations, but not honestly we're not going to do too much with kinematics here. But if we calculate something's final velocity, maybe we could do a kinematics problem with it. But honestly, we're not going to use it that much. Okay. So, let's just see when you all think of the word momentum. This question is basically what comes to mind? What is momentum? And to that end, which of the following has the most momentum? A football player running, a parked car, a baseball getting tossed at you, or a car going 10 meters per second? Which of these do you think has the most momentum? I have not defined the term yet. The whole point of the slide is to show you kind of know what momentum means. You have a sense of what it means. You've heard this word in your life before. If you've ever watched any sports broadcast, I'm sure they use this word all the time. Ooh, interesting. I am getting different answers. That's exciting. That's interesting. You never know what to expect until you get responses. All right, we'll go to a minute 05. This is one of those, just go with your gut. Don't overthink it. In 5, 4, 3, 2, 1. All right. So which has the most momentum? Here's the answers. The answer is going to be a car going 10 meters per second. And what I'm going to teach you, so the next slide is going to be the definition of momentum. So momentum is made up. Momentum, like energy, is made up. It's something that someone realized, if I do this math, this thing is conserved. If I do this math and have a bunch of objects and I find their momentums and then they do a bunch of things, they run into each other, and I calculate the momentum at the end, we find that my starting momentum equals my end momentum. Again, a math thing, it just emerged like energy. To that end, my hand-wavy definition of momentum, because it's a hard thing to define, is how hard it is to stop something. If it has a lot of momentum, it's hard to stop. If it doesn't have much momentum, it's easy to stop. That's a very hand-wavy, that is not a scientific definition, but it's kind of my sense when I think momentum. That's conceptually what I think about, how hard it is to stop. Here's the more formal definition. It's a measurement of a mass in motion. If you literally just take those two things, mass is mass, motion is velocity, momentum is mass times velocity. So really the kind of scientific definition of momentum is an object's mass times its velocity, which doesn't really tell you much. So that's why I have this hand-wavy definition, not scientific in any fashion, but it kind of is accurate. How hard it is to stop something. That's the way I remember what momentum is. It's just m times v. The symbol for it is p. P for momentum, obviously. No, it's not obvious at all. I have no idea why it's p. But p is the symbol for momentum, lowercase p. Someone decided at some point there's a reason. I don't know what it is. These are vectors. Notice the little hats, the little arrows above the p, the little arrow above the v. Mass does not have a vector associated with it. There's no direction to mass. So the direction of momentum is the direction of velocity. It's the same exact direction. If something's going to the right, it has momentum to the right. If the thing's going up, it has momentum up. So, momentum, really straightforward. M times v. No fuss, no muss. Just make certain you remember these are vectors and we have to treat them as such. If we want to combine two objects' momentum, we will combine the x components of momentum. We will combine the y components of momentum. You get the x and y, you do Pythagoras theorem to get the total momentum. So much fun. But really, really a straightforward m times v. That's it. Mathematically very easy to do. And literally this entire PowerPoint is just working with momentum. All right. So, let us practice. And the units for momentum, you're like, those are some weird looking units. Again, because momentum is made up, it literally just comes from the math. The units for mass are kilograms. The units for velocity are meters per second. Ta-da, you just derived the units for momentum. You multiply them together. How fancy. Anytime you all have units that look like a whole bunch of variables plugged together, that's because it's literally just from the math. Just take the units that make up that variable, do whatever the math says, and you get the unit. All right. Cool. Let's math. What is the momentum of a 0.5 kilogram baseball traveling at 10 meters per second? It's kind of slow. 10 meters per second is like, oh, I say kind of slow. That's kind of fast. 25 meters per second. That ballpark, 23 meters per second. Oh, no, actually someone told me if you take meters per second and you multiply it by, I think it's 2.2, that gives you miles per hour. I think. Let me fact check that. 10 ms 2 miles per hour. Yeah, 22.36. So if you just multiply meters per second by 2.236, you get miles per hour. That's kind of handy. All right, we'll go to a minute. Oh, and the grader said he should definitely have the free response done by next week. So, woo. Once I get those, it'll take me a day or two just to curve them, import them, that kind of thing. All right, we'll close this out in 5, 4, 3, 2, 1. Y'all did a great job of multiplying 0.5 times 10. It's 5. Great job, everyone. P equals MV equals 0.5 times 10 equals 5 kg ms. Now, will I be mean and on the test put an answer of 5 kg per m? Will I be mean and do the following? Have 5 joules and this answer? Yes. Because momentum is not energy, and if you tell me it's 5 joules, that's energy. And it may not seem like a big deal for getting your units, but it's the difference between calling an animal a dog and calling an animal a cat. They're both animals, but a cat's not a dog. If you do not put the right unit, you are telling me that you calculated energy, and again, may not seem like a huge deal, but you need to be accurate in how you represent things. If you're doing engineering, and you tell someone you got a number, 500 joules, they're going to think you're talking about energy. If you meant to be talking about momentum, they're not going to know that unless you said the word momentum. So, you need to be accurate in how you describe things. Units are an important part of that. The units, 5 joules and 5 kilograms times meters per second mean vastly different things, even though it seems like just a tiny little thing. It's a big deal. Units matter a lot. All right, so what's the point of momentum? Why do we care? It's a really cool thing that no matter what happens in the collision, it's conserved. No matter what happens, energy doesn't have to be conserved for momentum to be conserved. And in every single collision or separation, momentum is conserved. M times V. If you can get the M times V of the momentum of every single object from either things colliding or exploding, what I start with is what I end with. For every single thing. Even if you add energy to the system, or energy is lost. So like an explosion. If I literally have a basketball, or I don't care what it is, a car, and I explode that car. So the momentum of a car that's just sitting is 0. If I explode that car, I've got pieces flying all over the place. The momentum of all of those pieces, it does not matter how big that explosion is. The momentum of all those pieces will add up to be 0. It's crazy. Doesn't matter how big or small that explosion is. Now, with the caveat, some hit the earth, so I guess we could suspend this thing in the air to make certain we're just caring about the car pieces. But yeah, if you have an asteroid in space and it explodes into 3 pieces, the initial momentum of the asteroid will equal the final momentum of all the pieces added together, no matter what, which is crazy. Yeah.
So, even if 2 things collide, their velocity changes.
Yep.
So it wouldn't still change the momentum?
It will, but the momentum will be conserved. If they get stuck together, momentum is conserved. If they kind of get stuck together and separate, momentum is conserved.
What do you mean by that?
M times V. Say I have one object and it breaks into 2. M times V of the one object, and say it breaks into 2, will equal M1V1 plus M2V2. The M, if you multiply M times V for every single object in the beginning, and you add them all up, that'll equal the M times V of every single object afterwards, no matter what happened. It's crazy. It's cool. This is why, and this connects to forces as well. If you are in space and you want to move, you have to shoot something away from you. By shooting something away from you, so say you're floating in space and you have your 0 velocity, you have no momentum. If I throw something one way, that object that I threw will have a momentum that way, and I'll have a momentum the other way to cancel it out, so that my momentum at the end is also 0. So if you want to travel in space, this is how rockets work. They shoot hot gas one way, rocket goes the other way. Momentum is conserved. You shoot a lot of small particles really quick, it makes a really big object move at some velocity based on that. So, yeah, it's super useful. You can also use it to find the force an object experiences, and I'll give you the derivation for that as well. And we'll do some math with that. Well, momentum is extremely powerful. Like the things you can do with it, just like energy is extremely powerful. I keep telling you all made up. Just because it's made up doesn't mean it's not useful. Energy, conservation of energy is incredibly useful. Conservation of momentum is incredibly useful. An easy case, if you know how much energy is in fuel, that gives you a sense of how high you can go in the rocket or how fast you can go. You can never end up with more energy than you started with. And yeah, again, momentum, all these different situations. So, really, really simple ideas that are extremely useful for actually determining how the world works. All right, so anytime you have a collision, momentum is conserved. Anytime you have things that separate, momentum is. If you have a bunch of objects, momentum is conserved. Just like that's a thing. A collision, I can guarantee you all that 99% of you know what a collision is. Probably more than that, but let's be conservative and say maybe 1 out of 100. Two things hit each other. That's a collision. It's exactly what you expect it to. There is no fancy definition in physics for a collision. It's just literally two things hit each other. Yeah.
The masses of those two objects.
Nope, don't have to be. And we'll do some problems where the masses are different. Oh, and you're wondering, let's see.
Arrows still represent, like they did.
Oh, yeah, I don't know how accurate the arrows are here, to be honest. I don't know how I feel about these arrows. Don't trust these arrows. This is just a random animation to show you things colliding and bouncing off each other. I'd have to do the math, to be honest, to determine whether or not this is accurate. And also the size doesn't necessarily correspond to the mass. One could be more dense and yada, yada, yada. Okay, so here's a nice little derivation. It's actually not too complicated. So Newton's second law, we start with Newton's second law, F equals ma. We're cool with that. The definition of acceleration is dv dt. That is literally the definition of it. So then we look at our definition of momentum. P equals mv. We just defined that. If we take the derivative of momentum with respect to time, we do it to both sides. We get dp dt. The derivative of momentum with respect to time is dp dt equals mass is a constant dv dt. Long story short, compare these two. They're the same thing. So the force that an object experiences is just the derivative of momentum with respect to time. It's a really simple derivation. Kind of a nifty one to look through, but it's literally just saying, what's the definition of force? It's ma, which is mdv dt. Oh, look, if I take the derivative of momentum, I get the same thing. And so what does this tell us? This tells us that the force something experiences is just equal to how much the momentum changes per second. So if you run into a wall and you have a certain velocity, and afterwards you have a different velocity, and you know how long it took for that to change, you can get the force. So this, and rearranging this, if we want to get the force, we're going to have to do an integral, because it's a dp, that's derivative. Opposite of a derivative is an integral. The change in momentum, aka dp, equals the integral. Do you want the entire change? And yeah, this is really, really useful. We'll do some examples of this. Yeah.
Wait, did you say force was momentum?
It's the change. Yeah, force is the change in momentum. Okay. Divided by the change in time. The change in momentum over time. Yeah, dp dt. Change in momentum over time. So this is super useful, and there's a lot of really interesting examples of this. Let's see. Do I have... I really hope I do. Yeah, good. I talk about the egg drop here at some point. I thought I did. We'll get to that. So we'll talk about some interesting examples of this. We define we call it this dp dt. We come up with its own word for it. This change in momentum over change in time. We come up with its own term. We call it the impulse. The impulse is literally just that dp dt, like the change in momentum. However much my momentum changes, that's the impulse. Sorry, I said dp. Literally just the change in momentum is impulse. Change in momentum is impulse. Take final momentum minus initial momentum, impulse. Why does it get its own fancy name? I don't know. Someone decided it was worth it. But if you ever hear someone use the word impulse, which you will, at some point, if you're in engineering, you'll hear someone use the word impulse. Impulse is literally just final momentum minus initial momentum. How much of my momentum go up or down? That's the impulse. It is nothing super fancy, just change of momentum. If I have a constant force, I can take it out of the integral. So right here, this kind of step here, if force doesn't change over time, so if force doesn't change over time, remember, change in momentum is J. If force doesn't change over time, I can pull it out of the integral if it's a constant, and this just becomes F times T, change in T. Again, nothing too fancy. So, what's cool about this whole, and then yeah, force can be change in momentum over change in time, assuming a constant force. Assuming a constant force. Again, in the real world, most forces aren't constant, but for you all, most forces will be constant to make your life easier. We'll assume a constant force pretty commonly. How do you know if the force is changing with respect to time? If I give you a function where the force has a respect to time to it. F of t equals 5t, whatever. Anyway, yeah, but it's cool stuff, y'all. Everything we've done so far is really simple. All the things we've introduced are just like, we haven't done any crazy math to derive these things. Literally all we said was P equals mv and we went from there. But the stuff we can do with this has really big consequences. So momentum is such a cool idea. You can do so much cool stuff with it. You can explain so many cool things for such a simple idea. That's why it's useful. Same with energy. All right. So, if you get in a car crash, any kind of crash, but let's just make it a car crash since I say steering wheel. In which case will your face experience a greater change in velocity? If your face hits the steering wheel, if your face hits an airbag, or in both cases you experience the same change of velocity. So you're in your car is going 30 miles per hour, you hit a wall. You are no longer going 30 miles per hour. In which case will your face experience a greater change in velocity? Is it if you don't have an airbag and it hits the steering wheel? Is it if you do have an airbag and it hits the airbag, or the change in velocity is the same? Doesn't matter whether or not the airbag goes off. I'm enjoying that I'm seeing different answers here. That's nice. I like that because then it means there'll be a cool aha moment for some of us. Okay. I will clarify, we are assuming your head is not bouncing off. Okay, it won't matter actually. It doesn't even matter if your head bounces off this object. We're saying at the end of the day, okay. So we'll go 5, 4, 3, 2, 1. So we are doing kind of an approximation. I say approximation. If your car is going 30 miles per hour and you hit a wall, yeah. Where's that question? Oh, sorry, you're fine. If you're going 30 miles per hour and you hit a wall, your car was going 30 miles per hour, i.e., you were going 30 miles per hour, you hit a wall, your car is now going 0 miles per hour. Every part of you is going 0 miles per hour after you hit that wall. Because your body's stopping. If your body is not going 0 miles per hour, the only way that wouldn't be, it's going to happen. Your body will stop moving. Either you get thrown for even if we said, oh, you weren't wearing a seatbelt and you fly out of the windshield and you hit the wall, you will still end at 0 miles per hour. If you hit a wall, you're going to stop. So to that end, it doesn't matter what your face hits it's going to stop moving. It's going to go from 30 to 0. Now, I didn't say how fast that was going to happen. At this point, I did not say, what is your acceleration? I just said, what's your change in velocity? Well, you were going, let's just say 15 meters per second minus 0 meters per second. At no point does it matter what stops your face. You're moving and then you're not. Now the question is, in which case will your face experience a greater force? Hitting the steering wheel or hitting an airbag? Or is it the same, both experience the same force? Let's clarify that last part. Same. In which case will you experience a greater change in velocity? And you have two ways to think about this now. I've given you two mechanisms to think through this problem. One today, one in the past. We'll use both explanations. And well, they both have the same explanation, honestly. They both come from the same math. Alright, so we'll go to 55 seconds. There's not too much to say about this. Alright, so 5, 4, 3, 2, 1. And this problem gets to the heart behind why does an airbag exist? So let's go with the thing I just taught you all. I just taught you, we're going to assume a constant force. It doesn't even matter if we do. We can it still will work out the same way. But just to make the math a little bit easier to show, I just told you for a force, if we kind of take the average force equals the change in momentum over change in time. Average. Well, let's go ahead and rearrange that. Pull out an m. So momentum is the change in mv over change in t. M is staying the same. We're assuming your face isn't breaking into a million pieces. At least if they are, they're all staying together. So we get that. We just said that the velocity, the change in velocity is the same in both cases. So what's different? The time. Everything in your car around crashes is all about increasing the time. If I increase the time of that collision, I decrease the force. If I increase the time is on the bottom. So if I increase the bottom, if I increase the change in time, force decreases. If I increase the time of the collision, I'm, according to this math, getting a smaller force. If I decrease the time, it's a larger force. When your face hits a steering wheel, it comes to a stop very quickly. That's a large force to make. I mean, it's literally the definition of force. How much acceleration? If your velocity changes really quickly, that's a high acceleration, i.e. a large force. Again, we can look at this the other way. F equals ma. Oh, look at this. M equals dv dt. Oh, wow, it's the same thing. Again, this is where the derivations kind of all came from. If your face goes from fast to not fast in a short period of time, that's a lot of force. Your cars, back in the day, they said, back in my, I don't know, I'm not old enough to say this, but someone who's older than me, back in my day, they built cars that were stronger. When they got into crashes, they didn't crumple, and they could withstand a crash. That was not a good thing, because then if you have two hard objects hitting each other, they will come to a stop very quickly. And that's not good for you, who's in the car. You want to extend the time of that collision. It is much better, well, and this I guess you can make argument. I'm going to go ahead and say this. You can disagree if you want. It is much better to have to buy a new car than to be dead. You can argue that if you want, but it is much better to have to spend a bunch of money to fix, your car gets totaled. Yeah, that sucks, but at least you're alive. So, crumple zones. Your car is meant to compress. Why is your car meant to compress? Part of it is absorb some of the energy. It does absorb some of the energy when it crumples. but also it literally just increases the time of the collision. I mean, if you have two squishy things that hit each other, the collision lasts longer. Whereas if you have two hard things that hit each other, they bounce off each other really quickly. So, anywho, cool stuff, y'all. Momentum. It explains things. It helps us understand the world that we live in. To this end, the classic, the egg drop experiment. We're not going to do it because I don't have that many eggs. But this is a classic, if you haven't done this at some point, it's fun. You can do it with anyone of any age. That's the cool thing about this. I've done this with high schoolers. I've done this with like 6-year-olds. The egg drop experiment, this is an exercise in what we just talked about. How do you make the egg not break? There is a set amount of force that the egg can experience before it breaks. When it experiences a certain force, it will break no matter what. So everything in the egg drop experiment, the egg drop challenge, is how do I reduce the force it experiences when it hits the ground? And so you think, what are the variables at play? What force will it experience? Well, it's going to experience a force of m, change in velocity, over change in time. So you literally only have two variables you can play with. You can either make the change in velocity left or less. Add a parachute. Make it go slower. So instead of hitting the ground at 10 meters per second, you hit the ground at 5 meters per second. I've decreased my delta V. I've decreased my force. Or you increase the time. You add cushioning. You increase the time of the collision. You increase the time. You decrease the force. That's literally your only two options. And ironically, if your egg bounces, that may actually be more force because then your delta V was down and then up, and direction matters for velocity. So you actually don't want bounce. Bouncing things experience a higher force than things that don't bounce, depending on the time. Because the change in velocity, it was negative when it was going down, it's positive going up. If you subtract, let's just make up an example here. Let's say your velocity when it's going down is -5. Let's say somehow it's a perfectly elastic collision and your egg acts like a bouncy ball, which is very odd. Won't happen, but let's just pretend it did. Final velocity minus initial velocity. So final velocity, let's say it bounces up with 5. Let's say it was going down with 5. Something that bounces experiences a higher force than something that doesn't. Again, assuming the time of that collision is small. So that's kind of interesting. Bouncy things experience a stronger force because you have to make them go the other way. That's hard to do. Anywho, so have fun with this. Oh, and this is completely, don't need to know this at all. And I haven't thoroughly tested this, but something that was interesting, you may be like, can I change the orientation of the egg and will that do much? In my very, very rudimentary experiment I did, and you can actually test this at home if you want, the egg was equally strong up, down as it was left and right, which is kind of weird. How did we test that? I put an egg and I just kept adding masses to it until it broke. So when it was vertical, it took the same amount of mass as when it was horizontal. I have not looked into this. That was just a very rudimentary experiment I did. You can do the same experiment at home. Literally just keep adding weight to an egg until it breaks if you have two eggs that you assume are the same. It was just kind of funny. I don't know. Doesn't have any value to you other than just interest. Yeah.
How much mass was it?
Oh gosh, I don't know. Gosh, I wish I did. It was a lot more than you'd expect. Eggs are really strong. You may think, oh, they're not that strong. They're so easy to break. You'd be, for a very thin layer of egg like that, again, test it for yourself. See how many grams/kilograms you can put on an egg before it breaks. It's more than you'd expect for something that's literally just a very thin shell. All right, so cool. All right, let's do a problem with this. So a 75 kilogram person is riding in a car. They're moving at 20 meters per second when the car runs to a wall. Calculate the force on the person if they're stopped by a padded dashboard, which is a very generous way of saying a dashboard, that compresses an average of 1 centimeter, not very much, not very padded, versus calculate the average force of the person if they're stopped by an airbag that compresses an average of 15 centimeters. All right, so let's write down our givens. We have the mass of a person. We have their initial velocity. we have their final velocity. We're going to assume that you don't bounce off the wall and start rolling backwards. And we have two distances. We don't have time. So that's kind of funky. We have two distances. Let's just call those x. This is how much... we'll call it delta x. Equals 1 centimeter equals 0.01 meters. Okay. And there's actually a few ways you can go about solving this problem. We can solve this problem with Newton's second law. We can also solve this problem. I mean, Newton's second law and what I just taught you are basically, they are the same thing. Change in momentum ends up being m times a. But whatever. Let's find the average force. F average. How are we going to do that? We got two options. They are literally the same thing, just written two different ways. We have F equals ma. And we have that whole F equals change in P over change in T. And let me just show you all what I mean by they're the same thing. If we're doing averages, we can just do changes. So acceleration is the change in velocity over the change in time. Momentum is defined as a change in mv over change in t. Oh, look at that. We get the same exact thing no matter what. Okay. And you immediately probably realize the problem. I don't have time. We can find time. Kinematics. We have how far it travels. We have my change in velocity. Now, the question here, and this is kind of where you have to make a decision, and the wording of this, it's maybe not necessarily clear. Do we want to, I mean, obviously it's accelerating. So, let's see. Do we want to find the acceleration? Well, let's try it both ways. Let's assume, we can find the acceleration. We have Vf squared equals Vi squared plus 2 delta x. This is one of our kinematics equations from way back when. We know delta x. Oh, I missed something, because otherwise you're like, what's the point of that? 2a delta x. So that's one option. We can find the acceleration and then just put it at F equals ma and call it good. That's one option, find the acceleration and do that. The other option, let's see, do we want to, is there another option really that we can use? I think this is the most reasonable one. The other one is, I guess you could maybe make the argument that if we take like the average velocity, but I don't like that. Let's find A. Let's find A. A is dv dt, so it's kind of all built in. So if we rearrange this, so A equals Vf squared minus Vi squared all over 2 delta x. Step 4, just find A. A equals 20, nope, other way around. That's a good point. I don't know why I put this in. This is still step 3. Yeah, it's like I put 4 twice. Step 3, I generally keep it in terms of, so we'll put step 4 down here. Step 4 is putting the numbers in. So we're going to find A, I'm going to do another slide because we're not desperate for space. Okay, so we're going to take this, we're going to find A. A equals 0 squared. Be very careful. One of the habits that can happen, and I almost made this mistake, I started to write it. The final velocity isn't always the bigger number, so be careful here. The final velocity is 0, not 20. It's a tiny little thing, but it's a really common mistake. It makes a big difference at the end. Basically, the difference between which way you put it, are you saying you're speeding up or slowing down? We're obviously slowing down. Yeah.
Why is not x negative?
That's a good, we're going to say that you're moving forward. Your final position is 0.1 meters farther than you started. We're going to say this car is moving to the right. So if we look at the person's face and we look at the dashboard, their face hits the dashboard, and then their face at a later time is slightly into the dashboard, so you move to the right. That's a good question. Yeah. So their face did move forward, so we said delta x is positive. That is a great question. It's always good to ask, should it be positive or negative? All right, so we get 20,000 meters per second squared negative. That's the numbers here are kind of silly. Did I? And let me double check that I didn't do anything weird. No, that's fine. That's a lot of acceleration. It's a little high, but at the same time, so how many G's is this? To give you a sense of acceleration, you take the multiple G. This is 2,040 G's. Yes, if your face experiences this much acceleration, it's going to experience it's not going to be good for you. Yeah, and then you just, put these in. Now, you just multiply that by 75. And yeah, you get 1.5 times 10 to the 6 newtons. Let's put that in a way that's easier to read. Scientific notation is great, but scientific notation also sometimes it's hard to get a sense of how big that number is. Yeah, I mean, it's a lot of newtons. You get accelerate. Obviously, if you have a high acceleration, you're getting a high force. Yeah.
You said that it was negative 20,000.
Yeah, so that gives you a negative acceleration. We could technically say this force is negative. That just says the force is to the left. Yeah, that your force is to the left. Yeah.
How many G's of force can you take?
So the human body as a whole, you get up to around 10 G's, you're going to pass out. Nothing's going to break on you, but the blood starts you run into problems breathing and stuff like that. In this case, you're reaching an acceleration that your bones will break. Your bones can handle quite a good amount of force before they break. But if you experience 10 G's holistically for prolonged periods of time, whatever the direction that G's is, your blood is going to go in that direction, which is kind of the concern there. So, yeah, it's an interesting problem. If you repeat this and you literally just replace it with 15, let's just quickly plug that in. That takes 5 seconds. So if we just replace this delta x with 15, everything is the same. So A for 15 ends up being 1,333, which is still a lot, but it's 20 times less than that. And I'd have to look up what your bones could experience before they break. It's going to be based on your mass as well and all that jazz. Yeah.
8,065 kilograms.
8,000, that's how much your bone can experience? 1 cubic. Oh, bone. Oh, interesting. Yeah. So even if you do hit an airbag, you can potentially suffer broken bones, but probably less. Okay, definitely less. All right. There you go, y'all. Cool stuff. Kind of go through these fun times. The 815?
Yeah.
That was if it compresses 15 centimeters instead. I'll write it out, but. Yeah, everything stays the same. Except now my distance is 15 centimeters. Yeah, it's a good question.
because the